You've been told the universe is crawling with aliens, but every time you point dishes at the sky, you get nothing but static. And that isn't a glitch, it's exactly what the math predicts. When you factor in ridiculous distances, razor-thin habitable zones, chaotic planetary systems, tiny radio windows, and the hard limits of light speed, we never hear from anyone stops being a mystery and starts being the default. In this video, you'll see why the galaxy can be full of life and still look empty to you, and why, for a species like ours at a time like this, actually finding intelligent neighbors might be close to impossible. But before we continue, please subscribe to the channel to give your support. Let's continue. You hear the Milky Way has 100 to 400 billion stars, and it sounds like a cosmic traffic jam. It sounds crowded. It sounds like if you just point a radio dish somewhere, you should hit someone. But that number is spread through a huge three-dimensional volume. Near the sun, the average stellar density is about 0.004 stars per cubic light year. That means if you take a cube of space, 1 light year on each side, the most likely result is no star inside it at all. Even if you scale that cube up to 1,000 light years on a side, you only expect a few stars in there. That is not a packed city. That is almost total emptiness. The distance to your nearest neighbor makes that clear. The closest star system, Proxima Centauri, is a little over 4 light years away. In kilometers, that is roughly 40 trillion. In miles, about 25 trillion. The average gap between nearby stars is around 6 light years, close to 60 trillion kilometers, around 37 trillion miles. Those are not next-door distances. Those are good luck ever meeting distances. Before you talk about aliens, before you talk about signals, this is the basic layout you are stuck with. A few isolated stars with huge stretches of nothing between them. At this point, you might say, fine, they're far, but we have light, we have radio. Those move at the speed of light. That should fix the distance problem. It sounds like a solution, but when you put real numbers on it, it is not. Light travels at about 300,000 kilometers per second, roughly 186,000 miles per second. That is physics' speed limit. Your radio signals, your laser beams, all of that is capped at the same value. Over human scales, it feels instant, but over interstellar scales, it is very slow. A radio signal from Earth takes a little more than 8 minutes to reach the Sun, a bit over 4 hours to reach Neptune, and more than 4 years to reach Proxima Centauri. If there is a civilization there and they respond immediately, a simple hello and hello back is an 8-year round trip. Stretch that to what we would normally call nearby on a galactic map, say 1,000 light years, which is just 1% of the Milky Way's diameter. Now one message takes 1,000 years to arrive and 1,000 years to come back. 2,000 years for a single exchange. That is longer than the history of most cultures, longer than most languages survive. By the time you get the reply, your civilization may have changed, its technology, its beliefs, or collapsed completely. So yes, light is fast, but the structure of the galaxy stretches those delays into timescales where conversation stops being a useful word. So you shift the question. You stop expecting live chat and say, okay, maybe we will not talk to them. But if the galaxy has many civilizations, their signals should still be flying around. We just need to be in the right place with the right detector. That sounds reasonable, but again, the volume of the galaxy quietly ruins that hope. Let's be generous and say there is one intelligent technological civilization for every 1 million stars. With 100 to 400 billion stars, that gives you something like 100,000 possible civilizations in one galaxy. On paper, that looks like a lot, but now you have to distribute those 100,000 points inside a disk about 100,000 light years across and a few thousand light years thick. The average separation between them is still thousands of light years. You can fill that disk with dots on a diagram, but each dot is still very far from the next. Signals spread out as they travel, their strength drops with distance, and they get buried in background noise. Even if every one of those civilizations is transmitting, their signals are extremely faint by the time they cross those huge gaps. Most of the time, your telescope is pointed at the wrong patch of sky, at the wrong time, at the wrong frequency. The default is that nothing lines up. When you actually run the numbers, we never detect anyone turns into the expected result, and we happen to hear someone becomes the rare, lucky exception. So you might try one more angle. We don't only listen for radio, we are also looking for planets, and we've already found thousands of exoplanets. That should give us a way to find life, maybe even intelligence. That is progress, but it doesn't change the basic problem. Your search is still incredibly shallow compared to what's out there. Right now, astronomers have confirmed just over a few thousand exoplanets, a bit over 6,000 in the latest counts. The galaxy likely holds hundreds of billions of planets, maybe more. So your current catalog is a tiny sample, way less than 1 in a million. You can list these worlds in a database, you can classify them, but statistically, this is almost nothing. You can't say, we've checked the galaxy, no sign of city lights. You've barely checked your immediate surroundings. On top of that, your best detection methods are not built to find intelligence. They're built to find planets. The transit method measures a small drop in a star's brightness when a planet passes in front of it. This works best for big planets close to their stars in very specific orbital alignments. It tells you a planet's size and orbit, not whether someone is building radio telescopes on the surface. The radial velocity method checks how a star's light shifts as planets tug it back and forth. It gives you estimates of mass and orbit, again with a bias towards massive planets. No skyscrapers, no power grids, no internet, just gravity and light curves. So when people say we've detected thousands of exoplanets and still nothing, that doesn't mean we've searched properly and failed. It means we've barely scratched the surface with tools that can't see what we actually care about. You're trying to answer, are there minds out there, with instruments mainly designed to answer how many planets are roughly this size and orbit this kind of star. Put all of this together and the first conclusion is blunt. When you ask, where is everybody? The most straightforward answer is, they're too far away and your tools are too limited. Space is not just big in a casual sense, it's organized at scales where even the speed of light feels slow, and your current search volume is microscopic compared to the whole galaxy. The geometry alone almost guarantees that you hear nothing even if the galaxy is not empty. And the disturbing part is, this is only level 1 of the problem, because even inside this huge, mostly empty structure, there's an extra twist, one that makes your odds even worse. You've basically only just started sending and listening for signals at all. Here's the next problem, and it's brutal. You started listening almost no time ago. On cosmic scales, your entire search for aliens is basically still in the loading screen. Right now, Earth has been leaking strong radio and TV into space for about a century. Call it roughly 100 years of serious, detectable noise. That creates a bubble around you, a sphere of radio waves about 100 light-years in radius. In kilometers, that bubble is around 950 trillion kilometers across. In miles, that is roughly 600 trillion. Sounds huge, until you put it next to the Milky Way. The galaxy is about 100,000 light-years across, which is on the order of 1,000,000 trillion kilometers. Your little bubble, the whole region where anyone could even in principle know you exist from your radio leakage, covers about 1,000th of the galaxy's diameter and an even tinier fraction of its volume. Almost every star in the Milky Way is still completely outside the zone where Earth has ever made a peep. So when people say, we've been broadcasting for decades, why hasn't anyone answered? The honest answer is, hardly anyone could even know you are here yet. Most of the galaxy has not received the news that Earth has technology. Your signal front, that expanding shell of radio, has barely left your local neighborhood of nearby stars. It gets worse, because even inside that small bubble, you are fading out. Early in the radio age, your transmissions were accidentally loud. Old TV towers, early military radars, giant broadcast antennas, they sprayed power in all directions. From space, that looked like a messy but strong beacon. Modern technology is doing the opposite. You moved your communication into tight beams, fiber optic cables, focused satellite links, low-power mobile networks. This is good engineering. It wastes less energy and leaks less signal. But for an alien civilization 200 light-years away, that good engineering is bad news. By the time today's leakage reaches them, it is so weak that it blends into the background noise. In power terms, it is less than the random static from their own star, their own planets, their own technology. You might think, aliens must have better telescopes than us. They'll see everything. Physics disagrees. No matter how sensitive your detectors are, you cannot break the laws of signal to noise. A weak, scattered signal spread across all directions gets buried. To them, Earth today is quieter than Earth in the 1960s, not louder. That raises the obvious question. If your outgoing signals are weak and short-lived, maybe you should focus on listening instead. Point giant dishes at the sky, scan for signals from others, and let them be the loud ones. This is what SETI tries to do. But here, the scale problem hits again. Your listening effort so far is tiny compared to the size and age of the galaxy. You have only scanned thin strips of the sky, for short periods, in very narrow ranges of radio frequency. Most SETI projects pick interesting bands, like the hydrogen line around 1.42 gigahertz, or the so-called water hole region between hydrogen and hydroxyl frequencies. The logic is, hydrogen is the most common element. Water is key for life, so maybe aliens will pick those bands. It's a clever guess, but it's still just a guess. Physics does not require anyone to use those frequencies. On top of that, telescope time is limited. You cannot stare at every star at every frequency all the time. You get hours here, days there. Meanwhile, the universe has been running for 13.8 billion years. Your total ear-on-sky time, integrated over all instruments and projects, is microscopic compared to that. It's like listening to random 1-second clips from a massive 13.8 billion year-long audio track and concluding the whole song is silent. The fact that you haven't heard a clear alien signal yet is not surprising. It's exactly what you would expect from such a small, biased sample. There's another, even harsher layer, and it has nothing to do with distance or technology. It's about timing. For you to detect an alien civilization's signals, a few things have to line up. They need to exist. They need to go through a phase where they use loud, detectable communication, like wide-area radio. They need to do that while you're listening, and their signals have to be crossing your position at the right moment. Think about your own history. You've had radio for about 100 years. Be generous and say the detectable phase lasts 1,000 years, with a few centuries of strong leakage before and after your peak. In a universe 13.8 billion years old, that's a narrow slice. For any one civilization, its radio bright window is a tiny fraction of cosmic time. Now say there's another civilization somewhere and they also have a 1,000-year radio phase. If their phase ended 1,000,000 years ago, all of their signals have already washed past Earth. They swept through your region long before you had any receivers. If their phase starts 1,000,000 years in the future, then right now there's nothing to hear, and your signals haven't reached them yet. You're like two people flashing brief lights at random times on opposite sides of a huge field. The odds that both lights are on and visible at the same time are very low. Even if the galaxy is full of civilizations that come and go, their active windows don't have to overlap. And if the radio loud phase is short, maybe because technology quickly shifts to quieter methods, or because civilizations don't last very long, then the number of civilizations broadcasting right now can be extremely small, possibly less than one on average in the whole galaxy. So when you put it all together, the picture is clear. You have a small, fading bubble of radio noise, a very limited and selective listening campaign, and a universe where civilizations may flicker on and off over billions of years. Your failure to find anyone so far is not strong evidence that nobody's out there. It's strong evidence that your search has barely started. You're not missing aliens because you're stupid or because they're hiding behind some clever trick. You're mostly missing them because, in cosmic terms, you only hit unmute a moment ago. On the timeline of the universe, your entire technological phase so far is a blink, and you're trying to catch another blink that might have happened millions or billions of years away in both time and space. And that leads directly into an even tighter choke point. Because even if life appears, and even if civilizations light up briefly with technology, getting from a simple microbe to a mind that can build a radio in the first place is its own brutal filter. The universe might be full of life, but the step from cells to intelligence, that might be the real bottleneck. How do you actually look for aliens when almost every tool you have is tuned for planets, not for people? Most of what you know about worlds beyond the solar system comes from a method that cares about geometry, not civilization. You stare at a star for months or years and measure its brightness very precisely. If a planet passes in front of the star from your point of view, the light dips by a tiny amount, then goes back to normal. That's the transit method. It's very good at picking up big planets that orbit close to their stars and happen to be lined up just right with Earth. From that brief dimming, you get the planet's size, its orbital period, and its distance from the star. That's useful, but notice what's missing. You don't get a direct picture. You don't see continents, oceans, or night-side lights. You don't see towers or power grids. The data tells you there is an object this big moving on this orbit, not there are skyscrapers here. This is why many of the early exoplanet discoveries were hot Jupiters and other large, close-in worlds. The method is biased. Big planet, short year, tight orbit, perfect alignment. Those are the easy wins. An Earth-sized world at Earth's distance is much harder to see this way, and if the orbit isn't lined up just right, you see nothing. If you rely on transits alone, then most habitable zone planets, even if they exist, will never show up in your data. The second main tool, radial velocity, has the basic limitation in a different form. Instead of watching a star's brightness, you watch its spectrum, the pattern of lines in its light. As planets orbit, their gravity pulls the star back and forth a little bit. That motion shifts those spectral lines slightly towards blue when the star moves towards you, and towards red when the star moves away. From that tiny periodic wobble, you can estimate how massive the planet is and how far it is from the star. Again, this is great for detecting the presence of a planet, especially if it's heavy, close in, or both. But here too, the information you get is very stripped down. You're not measuring oceans, weather, forests, or factories. You're seeing a star being pulled by something and inferring the planet's mass and orbit from that. The method is naturally better at finding big planets, the ones that make the star wobble more. Small, Earth-like planets, especially far from the star, leave much weaker signatures. So your catalogs fill up with super-Earths and gas giants, because those are easy, while the subtle, potentially more interesting Earth twins are buried in the noise. Nothing in the radial velocity data tells you if anyone down there is sending messages, or whether the planet even has a solid surface you could stand on. You might point to the next step and say, okay, but we are starting to look at atmospheres now. That should help. This is true, and it is a real leap forward, but it is still at a very early stage. Using instruments like Hubble, large ground-based telescopes, and now the James Webb Space Telescope, astronomers can sometimes separate a tiny bit of the planet's light from the star's light, especially during transits. By spreading that light into a spectrum, they can look for the fingerprints of molecules in the atmosphere, things like water vapor, methane, carbon dioxide. This is how targets like K2-18b, TRAPPIST-1e, and others ended up in headlines. People talked about possible biosignatures, gases that might hint at life. But those early claims have already been pulled back, argued over, or heavily qualified. In the case of TRAPPIST-1e, one of the most hyped, potentially habitable planets, newer data suggests it may not have a stable atmosphere at all, thanks to strong radiation from its star. If you're struggling just to confirm this planet has any atmosphere, you're nowhere close to confirming this planet has industry, electricity, and a technological species on the surface. Because of that, the whole field of technosignatures sits in a strange place. The ideals are creative, but the practical tools are weak. People talk about looking for city lights on the night side of exoplanets for unnatural illumination. They talk about spotting industrial pollutants, chemicals that do not occur in large quantities without factories. They talk about waste heat from gigantic structures that harvest the star's energy, like Dyson swarms. On paper, these are all ways to detect technology without hearing a radio signal. In reality, every one of these searches demands extreme sensitivity and long observing times. City lights on a planet tens or hundreds of light years away are drowned by the glare of the star and the limits of your telescopes. Exotic pollutants in an atmosphere are hard to separate from natural processes and measurement noise. Waste heat from megastructures, if it exists, has to be picked out from all the normal infrared glow of dust, stars, and gas. And underneath all of it is a hidden assumption that alien technology would be built on similar scales, use similar energy, and leave similar fingerprints to your own. If they organize their infrastructure differently, or if they are much more efficient, the signals you are looking for might never appear. So, from the top down, your main methods are tuned to answer simple questions. Is there a planet here? How big is it? How fast did it orbit? Does it have some kind of atmosphere? Those are important steps, but they stop far short of, is there someone there who can think, build, and talk? You're trying to work out the existence of minds using instruments that were designed to count and weigh planets. Until your tools change by orders of magnitude, until you can directly image Earth-sized planets, read their atmospheric chemistry in detail, and maybe even see surface features, finding intelligent life is not just difficult, it's outside the intended design of your current hardware. And even if you someday reach that level of precision, there's still a deeper obstacle waiting underneath, because it's not enough for a planet to exist and be detectable. It has to sit in a very narrow set of conditions where liquid water, a stable climate, and long-term habitability are possible at all. And that window is far thinner than most people think. The phrase habitable zone sounds like a safe region where life can easily thrive, but the reality is that it's a very narrow knife edge. For a star like the Sun, the textbook habitable zone is a distance where liquid water can exist on the surface of a rocky planet. That works out to something like 0.95 to 1.4 astronomical units, roughly 140 to 210 million kilometers from the star, around 90 to 130 million miles. Move a planet a bit closer in, and you start pushing toward a runaway greenhouse where the atmosphere traps more and more heat until the oceans boil. Move a bit farther out, and you risk freezing the ocean solid over long timescales. That's before you even add the real complications. Because distance alone is not enough. The atmosphere matters. A lot. Too much carbon dioxide and other greenhouse gases, and you overheat. Too little, and you freeze. The planet's rotation rate matters because it controls how heat is moved from day to night and from equator to poles. The magnetic field matters because it shields the atmosphere from being stripped by stellar wind and radiation. Plate tectonics matters because it recycles carbon and stabilizes the climate over hundreds of millions of years. When you put all of this together, the real Earth window inside the classical habitable zone gets brutally small. You don't just need the right distance, you need a very specific set of physical and geological properties to line up and stay stable for billions of years. So if the target is that tiny, you might hope that at least the universe keeps throwing lots of darts at the board and making plenty of Earth-like planets anyway. But when you look at actual exoplanet data, you see something else. Most real systems do not look like your mental picture of the solar system at all. The most common types of planets we've found so far are things we don't even have here, super-Earths and mini-Neptunes, with sizes and compositions between Earth and Neptune. Many systems are extremely compact, with multiple planets packed closer to their star than Mercury is to the Sun, completing orbits in just a few days. On top of that, a lot of these planets orbit stars that blast them with high-energy flares, or sit in configurations where tidal forces twist and heat them. Your simple idea of another Earth 1 AU from a Sun-like star with a calm climate is not the default. It's the weird case, the outlier. The cosmic norm seems to be messy. Hot inner planets, eccentric orbits, strong radiation, and planet types that don't match anything in your home system. When people casually say there must be millions of Earths, they're skipping over the fact that most of the planets you actually see are nothing like Earth. You might then look at red dwarf stars and say, fine, maybe we won't find twin Earths around Sun-like stars, but red dwarfs are everywhere. That gives us more chances. Red dwarfs do dominate the galaxy. They're about 70% of all stars. They live a long time, trillions of years, which sounds good for life, but their habitable zones are extremely close in, maybe 0.05 to 0.2 AU, just a few million to a few tens of millions of kilometers from the star. At those distances, the physics gets nasty. Planets that close are often tidally locked, with one side always facing the star and the other side in permanent night. That sets up extreme temperature contrasts, one hemisphere baked, the other frozen. The thin band in between may be more moderate, but the climate is hard to stabilize. On top of that, young red dwarfs flare a lot, throwing out bursts of X-rays and charged particles. Even older ones can stay magnetically active for billions of years. Any atmosphere has to survive constant assault. Habitability around red dwarfs is not impossible, but it is not a simple, oh, they're small and common, so that solves it situation. You trade one set of problems for another, and the margin for a stable, long-term biosphere is still small. That brings up another uncomfortable point. Even when a planet sits in the right distance range and looks just right on paper, its atmosphere can still be in trouble. We are already seeing hints of this. Systems like TRAPPIST-1 were once held up as prime real estate, multiple Earth-sized planets in or near the habitable zone. Then more detailed studies started to show that some of those planets, like TRAPPIST-1e, may be losing or may already have lost their atmospheres under relentless stellar radiation. Without an atmosphere, you lose surface pressure, you lose temperature regulation, and over time you lose your oceans as water molecules break apart and hydrogen escapes into space. For intelligence to emerge, you do not just need an atmosphere for a few million years. You need billions of years of relative stability, with enough shielding and feedback mechanisms to keep liquid water around while life evolves from simple chemistry to complex multicellular organisms and then to technological cultures. That's an enormous demand on a chaotic system that is being hit by flares, impacts, internal geological shifts, and long-term changes in stellar output. Atmospheres are not guaranteed. They are vulnerable, and when they go, any surface life that depends on liquid water goes with them. So yes, life might start easily in many places. Microbes in subsurface oceans, under ice, in deep crusts, or in short-lived surface seas might be very common. But the specific conditions that allow a technological species to sit under a stable sky on a solid surface with liquid oceans for billions of years are not just rare, they are extremely fragile. You need the right distance, the right atmosphere, the right magnetic field, the right internal geology, and the right star behavior all lined up and kept in balance over most of the age of the planet. And even if you get all of that right on the planet itself, that is still not enough, because the planet does not float in isolation. It lives inside a planetary system where giant planets migrate, orbits drift, and debris flies around on unstable paths. The next layer of bad news is that whole systems, not just single worlds, can be hostile to long-term stability. Gravity turns many planetary systems into slow-motion war zones, and that war can wipe out your just right planet long before its life ever gets a chance to reach intelligence. Planetary systems are not calm clockwork models. They are long-term gravity fights, and that fight can quietly erase your best chances for life before anything complex ever appears. For a long time, astronomers assumed other systems would look basically like ours, small rocky planets inside, gas giants outside, everyone on mostly circular, stable orbits. Then the first detailed exoplanet surveys came in and blew that picture up. We started finding hot Jupiters, planets with roughly Jupiter's mass, but orbiting their star in just a few days, much closer than Mercury is to the Sun. You do not get a gas giant forming that close in. The disk is too hot and thin. The best explanation is migration. These giants probably formed farther out and then spiraled inward over millions of years, dragged by the gas disk or nudged by other planets. That inward drift is not gentle. A giant planet moving through the inner system throws everything else around. Smaller, rocky planets and planetesimals either get scattered into new, often eccentric orbits, crashed into each other, or tossed into the star. Some get ejected completely, turned into rogue planets drifting in interstellar space. If you had an early Earth-like world in that zone while a hot Jupiter marched through, there's a good chance it got destroyed, swallowed, or kicked into an orbit where liquid water is impossible. The neat layout you see in school textbook diagrams is not the rule. It is one quiet outcome in a long list of possible wrecked architectures. Even if you don't have a hot Jupiter slicing through the inner system, just having multiple planets is enough to create chaos over long timescales. Gravity is unforgiving. When you put several planets around a star, they constantly tug on each other. For a while, the system can look stable, but over hundreds of millions or billions of years, those small tugs can add up. Orbits can slowly stretch into ellipses, tilt, or resonate. At a tipping point, you get gravitational pinball. One planet gets pumped into a highly elongated orbit, starts making close passes by others, and then everything goes unstable. In those scenarios, planets can get thrown into the star, hurled far out into cold space, or smashed together in giant impacts. If your habitable zone planet gets dragged into a more eccentric orbit, it can swing from frying near the sun to deep freeze far away. That's not good for a stable biosphere. For intelligence to evolve, you need a world that spends billions of years in a relatively calm, nearly circular orbit inside that narrow habitable zone shell. Too much dynamical chaos, and that world either never forms in a safe orbit or it doesn't stay there long enough for complex life to develop. Our own solar system carries scars from this kind of early violence. The cratering record on the Moon, Mars, and Mercury point to a phase called the Late Heavy Bombardment, roughly 4 billion years ago. During that period, giant planet migration and resonances likely disturbed large reservoirs of asteroids and comets, flinging them inward in huge numbers. For tens of millions of years, inner planets were hammered by impacts. Each big hit can melt crust, boil oceans, and reset anything fragile living near the surface. If some early biosphere was trying to get started on Earth before that, it got reset, maybe more than once. From the perspective of intelligence, that bombardment is a hard filter. You cannot support evolving brains and complex ecosystems on a planet that keeps getting sterilized by continent-sized impacts. You need the bombardment phase to end and then stay low enough for billions of years. Earth appears to have gotten that lucky break. In many other systems, the chaos may never fully settle, or a later instability could restart the bombardment and wipe the slate clean again. Every extra round of that chaos cuts the odds that a planet gets a long, quiet window to climb from chemistry to consciousness. And even if a planet survives migration, pinball, and bombardment, it still faces the fact that stars do not stay the same forever. As stars age, they change. They swell, brighten, and eventually leave the main sequence, turning into subgiants and then red giants. Recent work, using data from missions like TESS and detailed stellar models, shows strong evidence that as stars swell, they often engulf close-orbiting planets. This is not a rare freak event. It looks like a standard chapter in stellar evolution. When a star grows large enough, its outer layers physically reach the orbits of its inner planets. Those planets spiral inward, lose orbital energy, and are either shredded or swallowed. Any world that might have once had oceans and cities gets erased in the process. From a long-term perspective, that means even successful systems, the ones that manage to support life and intelligence for a while, have an expiration date stamped on them by their parent star. Long before the universe ends, the inner regions of many systems are literally eaten. So when you take the whole picture of a planetary system seriously, the default story is not billions of years of gentle stability. It is violent formation, migration, chaos, bombardment, and eventual destruction, with maybe a narrow temporary calm in the middle, where a few lucky planets get conditions good enough for complex life. You are asking the universe to maintain something close to a precision clockwork for a huge span of time, long enough for a species that starts with stone tools to climb all the way to radio, rockets, and telescopes without being knocked back to zero or wipe out. Most of the time, that will not happen. Orbits will drift, impacts will hit at the wrong moment, giants will migrate through the wrong region, stars will flare too hard or swell too fast. The rare cases where everything lines up and stays balanced are the ones where intelligence can even appear as an option, let alone become detectable. And even if a planet survives all of that, even if it holds a stable climate and a complex biosphere, you still run into a brutal timing problem at the galactic scale. Civilizations are not permanent. They turn on and off in time, they have windows where they can communicate, and those windows are tiny compared to the age of the universe. That means your odds of overlapping with anyone else, right now, are even worse than all the physical filters suggest. You are not just dealing with dangerous planets and unstable systems, you're also dealing with tiny time slots where minds like yours briefly light up and then vanish. Here's the next problem. Even if the galaxy is full of civilizations, most of them are not just far from you in space, they are disconnected from you in time. Start with the basic timeline. The universe is about 13.8 billion years old. The Milky Way has had stars and planets for more than 10 billion years. Earth formed around 4.5 billion years ago. complex animals have only been around for a few 100 million years. Humans with agriculture, cities, writing, that's on the order of 10,000 years. Humans with radio and electronics, about 100 years. Put that on a 24-hour cosmic day. The universe starts at midnight. Stars, galaxies, planets build up over the full day. Earth shows up in the late afternoon. Complex life shows up late evening. Human civilization walks in minutes before midnight. Your entire radio and digital era is the last tiny fraction of a second before the clock hits 24:00. That is when you started shouting into the dark and listening for anyone else. So, what happens when you drop civilizations, with their own short tech phases, onto a timeline that long? You do not get a smooth, constant galaxy of radio noise. You get brief flashes. If a typical technological civilization stays advanced and visible for, say, 10,000 years before collapsing, going quiet or changing into something undetectable, that sounds generous from a human point of view. 10,000 years is longer than any current culture, longer than any present country has existed. But compared to billions of years, it's tiny. 10,000 out of 1 billion is a ratio of 1 in 100,000. Out of 10 billion, it's 1 in a million. For any given planet, the chance that you catch it specifically during that narrow 10,000-year tech window is extremely small. Now, spread that across the whole history of the galaxy. Different stars form at different times. Planets cool and stabilize at different times. Life, if it appears, takes its own path. Some worlds may reach intelligence earlier, some much later, some never. Each one, if it gets to high technology at all, has a short slice where it's loud enough to notice. Those slices are scattered all over a 10 billion year timeline. Most of them will not overlap. That means the typical situation is not many civilizations broadcasting together. It's lots of civilizations appearing at different times and then disappearing again, rarely sharing the stage. And even if you accept that, you might say, fine, but the galaxy is big, there must be enough of them that some overlap with us right now. This is where distance magnifies the timing mismatch. Take a civilization 10,000 light years away. If they died out 9,000 years ago, you still wouldn't know that. The last signals they sent near the end of their tech phase are still on the way to you. They won't reach you until another 1,000 years. If you point a radio telescope at their star today, you're looking 10,000 years into their past, and in that past, they may still be alive and broadcasting. You see the echo of a civilization that no longer exists. Reverse it. If their first radio broadcast is going to happen 9,000 years from now, then as of today, there is nothing to hear, and your signals will not hit them for another 10,000 years. You look at their star now, and it seems silent. But in their own present, they don't even know they're about to become intelligent life in your sense. You and they are always out of sync. Light travel time means you never see another civilization as now, you see them as then, shifted by thousands or tens of thousands of years. Combine that with a tech window that might only last 10,000 years or less, and the chances of your loud phase overlaps with theirs, while your signals are actually crossing the same region of space, are tiny. You are essentially trying to have a conversation with someone who speaks once every million years, using messages that take thousands of years to travel. You might hope that very advanced civilizations solve this by building long-lived structures, giant engineering projects that survive even if the society falls down. That would give you something like archaeology in the sky, evidence that remains visible long after the builders are gone. People talk about Dyson spheres, star-encompassing swarms that harvest huge fractions of a star's energy, or other megastructures on stellar or galactic scales. In principle, these should show up as weird signatures. For example, stars that are dim in visible light, but bright in infrared, because their light is being converted to waste heat. The problem is the universe is messy, and time still works against you. Dust clouds, star-forming regions, normal galaxies all produce lots of infrared emission. Separating alien megastructure from boring astrophysics is hard, and any structure that is not actively maintained will decay. Orbits drift, collisions happen, components fall into the star or evaporate. Over millions or tens of millions of years, a once clean artificial pattern can blur into something that just looks like random dust and gas. The universe preserves light from distant galaxies very well, but it doesn't preserve technology in a neat, labeled way. Even if an advanced species filled part of the galaxy with engineering, then died out hundreds of millions of years ago, you might only see weak hints or nothing that you could confidently call artificial. So when you ask, why can't we find them? One honest, grim answer is simple. You might have already missed most of them, or you are too early for the rest. Civilizations in the past may have burnt bright and vanished long before Earth had oxygen in its atmosphere. Civilizations in the future may not even have formed their first cells yet. You are listening during one short, quiet stretch of a 13.8 billion year story, with tools that have only been around for a century, and you're hoping that another short, fragile window around some other star happens to line up with yours and send a clear, unambiguous signal across thousands of light years. Most of the time, that will not happen. The default is that you are alone in your time slice, even if you are not alone in the full history of the galaxy. And as bad as that sounds, there's still a deeper bottleneck underneath all of this. Because before you even talk about timing, wars, or megastructures, you have to get from basic chemistry to a mind that can build a radio at all. Life might start easily, but turning microbes into a technological species looks like a slow, uncertain, and maybe extremely rare upgrade. People like to say life finds a way, but they almost never ask the harder question: does intelligence actually find a way? Or did it just barely scrape through once, here, by accident? Look at Earth's timeline in plain numbers. The planet forms about 4.5 billion years ago. The surface cools, oceans condense, and within a few 100 million years, there's microbial life. Simple cells, already doing chemistry. So the first step, going from sterile rock and water to bacterial-level life, might actually be fast and fairly easy, at least under Earth-like conditions. But then, everything slows down. Complex multicellular life, big bodies with tissues and organs, does not show up until more than 3 billion years later. Technological intelligence, a species that can build radios and rockets, appears only in roughly the last 100,000 years, a tiny fraction of the planet's history. If you take Earth's 4.5 billion years and treat it like 4.5 billion minutes of building a house, almost all of that time goes into the foundation, walls, plumbing, and structure. The last 30 minutes are where you finally install electricity and turn the lights on. So yes, life started fast, but the step from microbes to minds took most of the clock. If intelligence was the natural destination of evolution, you would expect it to show up earlier and maybe in more than one lineage. It did not. It took billions of years and a specific, messy sequence of events. That brings up a key point that people often gloss over. Evolution is not trying to produce intelligent beings. Natural selection has one basic rule. Traits that help you survive in your environment tend to spread. Traits that don't get removed. There's no built-in goal like reach computers or start a space program. If being smart helps you grab food or avoid predators in a certain niche, fine, intelligence gets rewarded. But if bacteria, plants, or simple animals already fill a niche efficiently without big brains, evolution has zero reason to push them toward high intelligence. Dinosaurs ruled the planet for around 150 million years. They dominated land ecosystems on multiple continents, in many forms, from fast predators to huge herbivores. They were extremely successful, and they did it all without radios, writing, or digital tech. From evolution's point of view, they were winning. They spread and adapted. There was no pressure that said, you must now invent Wi-Fi. Intelligence in the human sense may be a rare side effect of particular evolutionary paths, not a guaranteed end state wherever life exists. And even when evolution does produce high cognition, that does not automatically mean technology follows. On Earth, right now, you share the planet with octopi, crows, parrots, dolphins, whales, and other species that clearly solve problems, use tools, recognize individuals, learn from each other, sometimes even play and deceive. Their brains are complex, their behavior is flexible, but none of them built a global civilization. The reasons are very practical. An octopus is smart, but it lives in water and has a short lifespan. It can't control fire safely underwater, can't smelt metals, can't store and transmit complex cultural knowledge over many generations with writing on dry surfaces. Dolphins and whales also live in water, and even though they may have sophisticated social structures, they don't have fine manipulators to shape tools, build machines, or wire circuits. Crows and parrots are clever and can use simple tools, but a beak and claws are not the same as a hand with multiple fingers and precise grip. They can modify sticks and use basic objects, but building an engine or a telescope is another level. If you copy this pattern onto other worlds, you get a clear warning. A planet could be full of advanced, complex life that has no path to high technology. Ecosystems might be dominated by efficient predators, social herd animals, or ocean dwellers with rich communication and memory, and still never produce radio telescopes. From their point of view, they're doing fine. From your point of view, they're invisible. So the real hurdle is not just get intelligence. The real hurdle is get intelligence that can go technological. That adds more conditions. You need a body plan with manipulators, something like hands, tentacles, or other structures that can hold, shape, and assemble objects with precision. You need an environment where you can control energy sources, things like fire, stored fuels, strong materials. You need accessible metals in the crust, not all locked deep below or dissolved in an ocean you can never touch. You need surface conditions where you can build stable structures, preserve information, and run long chains of trial and error experiments. Take away just one of those pieces and the ladder breaks. Picture a smart species on a planet that is mostly ocean, with very little land and no easy access to dry fuel. They might never learn to use fire at scale, which means no metalworking, no chemistry labs, no silicon chips. Or picture a land species with great brains but very limited manipulators, maybe hooves or flippers, no fine grip, and no way to make complex tools. Or picture a world where the climate swings violently every few thousand years, wiping out settled agriculture before complex societies can take hold. In every case, you might get intelligence, but you do not get industrial technology. The civilization stalls at a level that never becomes visible across space. On top of the physical constraints, you also need time and cultural continuity. A species has to move from stone tools to metallurgy, to engines, to electricity, to electronics, to radios, and beyond, without being knocked back to zero too often by disasters and without losing essential knowledge in wars or collapses. You need stable surplus food to support specialists, people who do science instead of hunting. You need writing or some equivalent system to store information reliably. You need social structures that let knowledge accumulate instead of being wiped clean every few generations. Every one of those is another filter on the path from clever animal to radio-capable civilization. Put all of this together and the picture changes. Life might indeed be common. Microbes might exist on countless worlds, especially in subsurface oceans, hydrothermal vents, or stable underground environments. Simple multicellular life might also be widespread on the right planets. But the combination you actually care about, the stack that goes planet in a narrow habitable zone, plus billions of years of climate stability, plus evolution that happens to favor big brains, plus a body with good manipulators, plus accessible energy and materials, plus culture that builds science and technology that reaches radio and beyond, that is not one step. It's a long chain of low probability wins. You won that chain once, here. That does not mean the same full sequence is happening all over the galaxy. Statistically, it might be very rare. You might be living on one of the few planets where the dice landed exactly right, and where all the fragile requirements held together long enough to get you to this point, sitting here asking why you don't see anyone else. And even then, even if some other civilizations out there also manage to win this entire lottery, there's still another harsh twist. They might not use the same tools you do to communicate, or they might move past your kind of technology so fast that by the time you start listening for radio aliens, they're already using methods your current instruments cannot detect at all. SETI has a hidden bias. You're basically searching for 20th century Earth copies and assuming they stay there. Most classic search strategies are built around broadband radio signals. Maybe narrowband beacons near the hydrogen line frequency, around 1.42 gigahertz, or short, bright optical laser flashes. The idea is simple. Hydrogen is common. Water is important. Radio travels well through space, so an alien civilization might use those obvious channels to say hello. But look at what that really assumes. You are betting that other civilizations sit around at roughly your current tech level for a long time, using the same tools you happen to develop in the same narrow slice of the spectrum, instead of quickly upgrading to something cleaner, more efficient, and much harder for outsiders to notice. You can see the problem just by looking at your own history. Early radio and TV blasted power in every direction. Now you use tight beams, satellites, fiber optics, and dense encrypted digital signals. The trend is clear. As tech advances, communication becomes more targeted, more compressed, and less leaky. A very advanced civilization will push that even further. They might route almost everything through local high bandwidth networks, underground cables, or tight laser links between stations. Or they might use channels like neutrinos or quantum networks, which can carry data but barely interact with normal matter. To anyone outside their systems, the spillover into space would be close to zero. Now, scale that up to something like a Kardashev Type 2 civilization, one that can use a large fraction of its star's energy. They have every reason to avoid wasting power on huge omnidirectional broadcasts. Energy is still a resource, even if they have a lot of it. It makes more sense to run ultra-efficient, local encrypted networks than to spray obvious beacons across the galaxy. From light years away, their signal footprint could be lower than your current leakage. They might look quieter than you do, even while running a civilization far beyond your understanding. So you try a different angle. You say, we won't listen for messages, we'll look for infrastructure. That leads to techno-signature ideas like Dyson spheres or swarms, giant structures orbiting a star and capturing much of its output. Physics says that if you capture a lot of starlight and use it, you eventually have to dump waste heat. That waste heat should glow in infrared. So the strategy becomes, search for stars that are oddly dim in visible light, but unusually bright in certain infrared bands, as if something is intercepting and re-radiating their energy. In principle, that works. In practice, the sky is full of natural infrared weirdness. Dust clouds around young stars, shells of material around dying stars, star-forming regions, normal galaxies with lots of dust. All of these show up as bright infrared sources with odd spectra. Distinguishing a true artificial pattern from all the normal clutter requires extremely precise measurements and careful modeling. A vague anomaly is not enough. You need hard, repeatable evidence that the spectrum cannot be explained by dust, gas, or known astrophysical processes. So far, every candidate has either faded with more data or stayed ambiguous. Megastructures, if they exist, are either rare, subtle, or designed in ways that do not match your expectations. And that's still assuming aliens use energy and communicate in channels you already monitor. There is no law that says they have to. They might encode information in modulated gravitational waves, in patterns of high-energy particles, in engineered bursts of cosmic rays, or in controlled short-lived transients that you would currently file under odd astrophysical event, and move on. These are channels you either barely detect or you do not systematically search for artificial patterns in them at all. In that scenario, your entire search effort is like tuning an old AM radio, scanning a narrow band of frequencies, and then announcing no one is talking on Earth, while everyone has moved to fiber optic cables, satellite internet, and communication modes your radio can't decode. The bottom line is awkward. It's not only that alien civilizations are rare or far away or short-lived. Even if they are common, close enough, and long-lived, you can still miss them completely because you are listening for the wrong kind of signal, built on your own short local tech history. You are locked into your toys and your assumptions, pointing antennas at a tiny slice of possibility space and calling the silence meaningful. So when you stand under the night sky and ask, "Where is everybody?" part of the answer is they may be talking all the time, just not in any way your current instruments and ideas can pick up. You are listening for the wrong instruments, in the wrong band, during the wrong part of the song. And underneath all of that, Even if you fixed your assumptions, even if you built perfect detectors and knew exactly what to look for, there's a deeper, non-negotiable barrier you cannot engineer away. The universe has a hard speed limit, and that limit does not care about your curiosity, your patience, or your desire for contact. Even if the galaxy is full of minds, the speed of light itself works to keep you apart. The hardest wall between you and any alien civilization isn't distance, it's the speed limit built into the universe itself, and that limit does not bend no matter how much you want it to. Relativity says one simple thing that matters here. Nothing with mass can reach, let alone exceed, the speed of light. Light does about 300,000 kilometers per second, around 186,000 miles per second. Try to push any ship with real mass toward that speed, and the energy cost climbs brutally. Even if you aim low and target just 10% of light speed, about 30,000 kilometers per second, roughly 67 million miles per hour, you hit mind-blowing numbers. At that speed, a trip to the nearest star, a bit over 4 light years away, is on the order of 40 years of travel time, and that's before you add the time for acceleration and deceleration, so your crew is not crushed by more than a few Gs. The energy bill to get a ship to 10% of light speed is not a bit more fuel. Kinetic energy scales with the square of speed, so when you multiply the speed by 10, the energy goes up by a factor of 100. For a payload with the mass of a large, modern ship, you're talking about an energy input comparable to decades of current total global energy production, all focused into one vehicle. And that's just to speed up. You need a similar amount to slow down at the other end if you actually want to stop instead of flying straight past your target. Every extra kilogram you add for crew, shielding, supplies, and structure makes that problem worse. And that's all before you deal with what the ship has to punch through on the way. Because interstellar travel isn't just an energy problem, it's a physics and engineering nightmare. Space between stars is not completely empty. There's gas, dust, and tiny grains of rock floating around. At ordinary spacecraft speeds in the solar system, these are mostly a nuisance. At 10% of light speed, each grain of sand has impact energy in the range of a high-caliber bullet or worse. Your hull isn't just moving fast, it is ramming into a constant stream of microscopic projectiles at tens of thousands of kilometers per second. A single unshielded hit can punch straight through and cause catastrophic damage. To survive this, you need serious protection. That could mean thick layers of sacrificial material on the front that vaporize and absorb hits, massive physical shields, or large magnetic fields to deflect charged particles. All of these solutions add mass. More mass means more energy to accelerate and decelerate. More energy means larger power systems or more propellant. Larger power systems and more propellant mean even more mass. The whole design spirals upward into a huge, heavy, extremely expensive craft that still spends decades crossing to the nearest star and remains vulnerable to events you can't predict ahead of time. So you might try to sidestep the crew problem and say, forget people, send probes. A robotic probe doesn't need life support, doesn't complain about a 100-year trip, and can be smaller and lighter. That definitely helps, and many serious concepts for interstellar exploration rely on this. But even if an advanced civilization floods the galaxy with autonomous probes, that doesn't mean you will see them, or recognize them, or still have any around you now. A cautious civilization might send probes that operate at very low power, only waking up occasionally to sample data in order to avoid drawing attention or contaminating young biospheres. They might deliberately avoid broadcasting anything strong, especially near planets with life, to reduce their footprint. Or they might program their probes to do a survey pass and then leave, or shut down instead of hanging around indefinitely. In that case, if one of their machines cruised through your solar system tens of millions of years ago, you would never know. Any small traces left on a moon or asteroid could be erased by impacts, erosion, or geological processes. Probes solve the logistics of travel, but they don't guarantee clear, persistent signals that a developing civilization like yours can easily detect. Even if you assume some species does solve the engineering, built ships or probes and travels widely, there's another limit waiting, on the social side. Big science fiction pictures often show galaxy-spanning empires, unified cultures controlling thousands of systems. Physics quietly tears that down. Communication is stuck at light speed too. If your capital is 1,000 light years away from some frontier colony, every message takes 1,000 years one way. A simple question and answer loop takes 2,000 years. You cannot run a centralized state with meaningful control over distant regions on those timescales. Orders arrive long after situations have changed. News of problems reaches the center centuries after they happened. Everything beyond a few nearby stars slips into practical independence, whether you admit it or not. So any real empire spread across hundreds or thousands of light years will fragment into separate cultures. They develop their own paths, their own technologies, their own priorities. Some may go quiet, some may collapse, some may change in ways that leave almost no detectable techno-signature. From your perspective, staring out with telescopes, what you see is not a unified, loud civilization, but scattered, disconnected histories, many of which never intersect with you in a way you can notice. Put this all together and the picture is harsh. Even if the galaxy is full of minds, and even if some of them overcome the engineering challenges of interstellar travel, the speed of light makes meaningful back and forth interaction between them almost impossible on human scales of time. You can't visit easily. You can't talk in real time. You can't coordinate large structures over thousands of light years. The universe is structured so that each civilization grows up in a local cage set by energy costs and light speed delays. And while you're stuck in that cage, fighting distance and delay just to talk to anyone, there is another layer of difficulty you cannot ignore. The cosmos itself is constantly throwing lethal events at planets and biospheres. Supernovae, gamma ray bursts, rogue impacts, long-term climate swings. All of these can reset or erase life, no matter how smart it gets. You probably feel like Earth orbits in a mostly calm, safe environment. But once you zoom out, you see that the universe spends a lot of its time trying to wipe biospheres off the board. Start with the big killers. Massive stars live fast and die as supernovae. When they blow, they dump huge amounts of energy, high-energy photons and particles into their surroundings. A nearby supernova can strip away ozone layers, spike radiation at the surface, and damage DNA directly. That alone can stress or collapse ecosystems. Then there are gamma ray bursts, GRBs. These are narrow jets of ultra-energetic photons fired out during some extreme explosions, like the collapse of very massive stars or mergers of neutron stars. If one of those jets happens to point at a planetary system, even from thousands of light years away, it can dump enough energy into the upper atmosphere to wreck chemistry, destroy protective layers, and increase surface radiation for long periods. Over billions of years, different regions of a galaxy get hit by waves of this kind of activity. Star-forming belts, clusters of big young stars, spiral arms passing through dense gas clouds. All of these create cycles where supernovae and possibly GRBs are more common. Every time that happens, planets in the wrong place at the wrong time can get their evolutionary clocks reset. A world that has slowly built up complex life over hundreds of millions of years can see that progress smashed down, not because of anything it did, but because a star tens or hundreds of light years away ended its life violently. Zoom out even more and you get another filter. Not every part of the galaxy is equally good for long-term habitability in the first place. Near the galactic center, star density is high. That sounds promising at first, lots of stars, lots of planets, but it comes with intense radiation backgrounds, frequent close encounters between stars, and a higher rate of disruptive events. Orbits can be perturbed more often. Comet reservoirs can be shaken up repeatedly, and the environment is flooded with energetic particles and X-rays from various sources. Far out in the galactic outskirts, the opposite problem appears. Star density is low, and metallicity drops. In astronomy, metals means elements heavier than helium, the stuff you need for rocky planets and complex chemistry. Fewer heavy elements means fewer solid worlds and less raw material for biology and technology. The result is what people call a galactic habitable zone, roughly a ring where conditions for long-term, stable rocky planets with atmospheres are better. Even inside that ring, things move. Stars orbit the galaxy. Spiral arms shift. Gas clouds drift. A system can move into and out of safer regions over billions of years. A planet might spend some epochs in a relatively quiet environment, then later pass through a rougher neighborhood with higher risk of radiation events and orbital disturbances. Now drop back to the scale of individual systems. Gravity doesn't just eject asteroids and shuffle planets around. Sometimes it throws entire planets out into interstellar space. When planets interact strongly or when a passing star gives a strong tug, a world can be kicked completely free of its star and become a rogue planet drifting through the dark. Whatever surface habitability it had is gone, unless there is some exotic internal heat source keeping subsurface oceans barely alive. Even bound planets that stay in their systems face constant risk of big impacts. Your own history shows that clearly. About 66 million years ago, a roughly 10-kilometer object hit Earth and wiped out most large land animals, including non-avian dinosaurs. That was likely triggered by long-period comets or asteroids perturbed from distant reservoirs, such as the Oort cloud, by subtle gravitational nudges over time. Passing stars, giant molecular clouds, or long-term orbital cycles can spike the rate of these extinction-level events. A single unlucky impact can end an entire branch of complex life, or at least force evolution to restart key ecosystems from scratch. Layered on top of impacts and radiation is climate instability. Earth has not been stable and mild for its entire 4.5 billion year history. It has had snowball Earth episodes where ice likely reached near the equator, turning the planet into a near global frozen state. It has also had hot periods where crocodile-like animals lived in what are now polar regions. These extremes came from complex feedback loops involving carbon dioxide, continental positions, ocean circulation, and sometimes large volcanism or impacts. The key point is how sensitive the system is. A slightly different balance of greenhouse gases, a different timing for a major volcanic event, a different tilt or orbit variation, and complex life might not have recovered in the same way, or at all. You got a particular sequence where the planet dipped into and out of these extremes without locking permanently into a frozen or overheated state. Now take that fragility and scale it to billions of worlds, each with its own chaotic mix of geology, atmosphere, orbital cycles, and random hits from space. Many of them will never sustain stable climates long enough for intelligence to appear. Some may go quiet, some may collapse, some may change in ways that leave almost no detectable techno-signature. From your perspective, staring out with telescopes, what you see is not a unified, loud civilization, but scattered, disconnected histories, many of which never intersect with you in a way you can notice. This leads to a blunt conclusion. Intelligent life is not only hard to start, it is constantly under threat from a universe that does not care about stability. There is no built-in protection that says, once a planet has minds on it, it will be left alone. Every world with a technological species on it is playing a long, improbable survival game against radiation bursts, orbital shifts, impact events, and climate swings. You are here because so far, Earth has threaded a narrow path through all of that. And even if a civilization survives these external blows, it still has to deal with another obstacle, one it builds for itself. High technology carries its own set of risks. Nuclear weapons, engineered diseases, uncontrolled climate change, unaligned advanced AI, resource depletion, social collapse, all of these can end or permanently shrink a civilization from the inside. So, after you account for the cosmic hazards, you still have to ask a darker question. Maybe the reason you do not see many technological neighbors is that most of them do not handle their own power very well. Even if the galaxy was packed with transmitters, your basic problem is that the universe is loud, and the thing you're hoping to hear is, by comparison, very quiet. Start with what your radio sky actually looks like. Pulsars, spinning neutron stars, throw out regular pulses. Quasars and active galactic nuclei pour out radio waves from the centers of distant galaxies. Normal stars, warm gas, and dust all contribute thermal noise. Planets with lightning storms add bursts and crackles. On top of that, you have your own mess. Satellites, radar, communication systems, all spilling power across a wide range of frequencies. When you point a radio telescope at the sky, you do not see a calm, empty background with one clear alien tone. You see a complicated mix of natural and artificial signals, a wall of static with patterns buried inside it. Now, drop an alien beacon into that. If some civilization is sending a narrow band signal, maybe at a steady tone to mark its presence, that signal will be weaker than many of the noise sources in your own environment by the time it reaches you. To pull it out, you have to integrate the signal over long periods. Point your dish at exactly the right spot, use the right frequency resolution, and process the data in exactly the right way. Miss any of those, and the beacon is just one more small fluctuation in a noisy spectrum that you will never revisit. And that's just one dimension, frequency. The real search space is much bigger. For every potential signal, you have to worry about multiple parameters at once. Frequency is one, sky position is another, where in that huge dome you point the telescope, and for how long. Signal duration, are you looking for a brief pulse, a continuous tone, a repeating pattern every hour, every day, every year? Modulation scheme, how the information is encoded, simple on-off keying, frequency shifts, complex digital patterns. Repetition rate, whether the signal cycles regularly or is triggered by events on their side. Each of these is a separate axis in the search. Multiply them together and the number of possible combinations becomes enormous. You simply do not have the hardware, time, or money to brute force all of it. You cannot scan the whole sky at all frequencies with all possible time resolutions all the time. So every real SETI project has to make choices. It picks a limited set of frequencies, a list of target stars or regions, a narrow range of signal types to look for, and short windows of observing time. That means by design, most of the possible parameter space goes untouched. If aliens choose a different frequency bands, a different modulation, a different duty cycle, you may never even set up your instrument in a way that can see them. On top of the physical limits, you also run into a psychological and practical problem: false positives. From time to time, radio surveys pick up something that looks interesting. A classic example is the WOW signal in 1977, a strong, narrow band detection near the hydrogen line that stood out from the background. It looked like exactly the kind of thing you might hope for, but it never repeated. Follow-up observations found nothing similar from the same region. Many other candidates have followed the same script: a strange signal that appears once, triggers excitement, then fails to show up again. Most of these turn out to be natural astronomy, instrument glitches, software issues, or interference from Earth-based sources, things like reflections off satellites, aircraft, or local equipment. But each time a promising pattern collapses into a mundane explanation or a non-repeatable event, it chips away at motivation. Funding agencies get more skeptical. Observers get more cautious about claiming anything. The field has to balance healthy skepticism with the need to keep looking deeper. And that is hard when clear wins are rare and ambiguous hints are easy. There's another catch hiding in the details of how information is sent efficiently. A signal that is maximally compressed and encrypted using modern or beyond modern techniques does not look like easy-to-spot structure. It looks like noise. In fact, that's one of the design goals. Good encryption produces outputs that are statistically indistinguishable from random data, unless you have the key or know the exact encoding method. So imagine a civilization that's even slightly ahead of you. They're unlikely to send raw, uncompressed, unencrypted data in big, obvious patterns, because that's wasteful and insecure. They'll pack information tightly and protect it. From your point of view, if you intercepted that stream, it would look like a slight increase in noise in some narrow band with no clear periodicity or pattern you can decode. Alas, they deliberately choose to send a simple, artificial-looking beacon just for the sake of being noticed. Their real communication channels will blend into the background. In other words, the more advanced and efficient they are, the more their signals hide in exactly the kind of random static your algorithms are designed to ignore. Put all of this together and the situation is clear. You are trying to pick out a faint, narrow, possibly encrypted signal in a sky full of bright, messy, natural, and human-made radio clutter, using instruments that can only test a tiny fraction of all the ways such a signal could be structured. You do not know the right frequencies, you do not know the right directions, you do not know the right time windows, and you do not know the right encoding. You have to guess, over and over, and accept that most of your guesses will be wrong, not because nobody is transmitting, but because the space of possibilities is huge and your resources are small. So when you ask, why haven't we picked up anything yet, the honest answer is that you are trying to do an extremely hard pattern recognition task inside a very noisy environment, with incomplete data, and with no guarantee that the patterns you are looking for are even the ones that exist. It is not just that the signal is faint, it is that the background is overwhelming and your filters may be tuned to the wrong features. This means that impossible to find is not exaggeration. It is a realistic description of your current situation. You are limited by physics, by engineering, by funding, and by your own assumptions. Even a galaxy full of transmitters could look empty from your one small vantage point with your present tools. And that leads to one more uncomfortable layer. Suppose you beat the noise. Suppose you find a clear sign that someone else is out there. You still have to ask whether they are going to be there for long, because high technology does not only let civilizations reach out, it also gives them more ways to damage themselves, to shrink, to hide, or to vanish completely. The lifetime of a communicative civilization might be short, not because the universe destroys it, but because it undermines itself. Once you finally admit how hard it is for intelligence to appear and survive external threats, you still have to deal with the darker possibility. Maybe the main thing that kills civilizations isn't the universe, it's their own technology. Any industrial civilization that keeps advancing is going to invent powerful tools, nuclear weapons, engineered pathogens, and global-scale industry that can destabilize climate, advanced AI systems that might not stay under control. These are not science fiction, they are natural byproducts of pushing engineering forward. You don't need a guaranteed apocalypse in that list, you just need a non-zero chance of serious self-inflicted catastrophe in every century. Stretch that over thousands of years, and even small per-century risks stack up into a high probability that something goes badly wrong at least once. It doesn't have to be total extinction. It can be enough damage to knock a society back to pre-industrial levels, wipe key infrastructure, destroy archives, and make rebuilding to the same level extremely hard. Even if outright collapse is rare, there are softer limits. Civilizations can hit ceilings long before they reach galaxy-spanning empire mode. You're already seeing early versions of this on Earth. There are hard constraints on fossil fuels, minerals, fresh water, arable land, and how much waste heat and pollution your biosphere can absorb. Energy use can't just grow exponentially forever on a single planet without consequences. Social systems also strain under complexity, inequality, and conflict. A civilization might push up against these resource and social limits, then level off, not by expanding explosively into space, but by leveling off into a long-term, lower-profile equilibrium. From the outside, that looks like a modestly advanced world with good tech, strong local networks, maybe some space infrastructure, but no huge beacons, no megastructures, no massive interstellar projects. Lots of worlds could end up in that state. Instead of a few loud Type 2 civilizations remaking their whole region of the galaxy, you get many quiet, bounded societies, each focused mainly on its own star system. They are advanced in the sense of knowledge and control, but they are not broadcasting their presence at scales you can see from light years away. On top of physical and economic limits, culture itself can move away from the kind of curiosity you are betting on. Exploration is not compulsory. A civilization that goes through brutal wars, failed early expansion attempts, or near extinction events might decide that reaching out is simply not worth the risk. They could build rich virtual environments and spend their time there. They could adopt philosophical systems that treat the outside universe as irrelevant, dangerous, or sacred and untouchable. They could enforce strict non-broadcast rules, either to avoid hypothetical threats or to minimize interference with other biospheres. The result is a society that might be technologically very capable, but psychologically turned inward. It maintains its infrastructure, maybe for millions of years, but it does not scream across the galaxy. It does not build giant, obvious structures just to be seen. It does not run loud, omnidirectional transmitters announcing, "We are here." From your perspective, with your limited telescopes and short observation window, it looks like nothing. A perfectly functional, long-lived civilization that has simply chosen not to look like a beacon. In the standard Drake equation way of thinking, all of this collapses into one term, L, the average lifetime of a communicative civilization, where communicative means detectable by others with tools like yours. If L is large, millions of years, you expect many civilizations to overlap in time and be visible. If L is small, a few thousand years or less, the odds collapse. And small can come from many directions, not just dramatic self-destruction. It includes societies that retreat into silence, societies that stabilize at low visibility, and societies that lose the ability or the will to maintain outward-facing technology. Once they stop broadcasting or building giant, obvious structures, as far as the galaxy is concerned, they have dropped out of the visible pool. If the typical L for radio bright, beacon building, mega structure constructing civilizations is only a few thousand years, then the number of such civilizations active at the same time in the Milky Way can easily be less than one on average. In other words, most of the time there are 0 or 1 civilizations you could, in principle, detect with tools like yours, and that one might not be you. That's what it means for civilizations to be self-limited or short-lived. They flicker on and then either burn out or dim themselves to the point where they blend into the background. So when you look up, see nothing obvious, and wonder if the universe is empty, there is another answer sitting in front of you. The universe might be full of civilizations that have already ended, collapsed into low-tech survivors, or turned inward and quiet. They are not missing, they are hidden by time, choice, and their own constraints. You will almost certainly never notice most of them. And even if some of them are still out there right now, stable, advanced, and watching, there is one more twist. Maybe you can't find intelligent life because your entire idea of what counts as intelligence is based on one species, on one planet. Alien minds might be so different that even if they're staring straight at the same universe, the way they think about communication, exploration, and meaning has nothing in common with yours. You keep asking where the aliens are, but you almost never ask what they would even be like in their own heads, and that blind spot matters. Start with something basic, senses. You navigate the world with vision, especially in visible light, plus sound and touch. So you take it for granted that any intelligent species will look up, see stars, and start wondering what those lights are. But that is a very Earth-specific path. An underwater civilization might never treat light as the main sense. Water blocks and scatters light, especially at depth. Instead, they could use pressure waves, low-frequency sound, chemical signals, or electric fields as their primary communication and perception channels. Their whole concept of far away might be limited to what those signals can cross reliably in their environment. Now think about a species that evolves in a very dense atmosphere. Under permanent thick clouds, they might see only a diffuse glow, no sharp stars, no clean night sky. Their myths, their science, their curiosity, all would be focused on what happens in their atmosphere, on their surface, underground, not in space. To them, worrying about distant objects beyond their clouds might sound like obsessing over something irrelevant. Cosmic curiosity is not guaranteed. It is a local product of your environment, not a universal law. Even if another species reaches science, builds theories, and measures physical laws, the way they organize that knowledge could be very different. Your physics and mathematics are built with a certain style, emphasizing reductionism, equations, and models that let you predict and control things at larger and larger scales. Another species might focus their intellectual energy on fine-grained ecology, on complex feedback systems, on internal mental states, or on computational structures that never manifest as giant machines. They could understand gravity and electromagnetism perfectly well, but see no reason to build megastructures or giant antennas. Their idea of advanced technology might be microscopic inside bodies and brains, or limited to precise control of local matter and energy flows. No city-sized radio dishes, no colossal orbital rings, no obvious Dyson swarms, just very refined management of their local environment that does not show up clearly from light years away. You also assume that communication, especially long-range communication, is a natural goal. You project your own instincts that once you become aware of the cosmos, you would want to talk, to explore, to announce your presence. A truly post-biological intelligence might see that differently. If you can convert matter into computation, if you can build dense substrates for thought, you can pack enormous amounts of experience and processing into a small physical volume. From that perspective, the best use of resources might be to stay local and optimize, not to send messages across interstellar distances with huge time delays. In that kind of value system, interstellar outreach looks like a bad trade. You spend energy to send messages that will take centuries or millennia to arrive to recipients you know nothing about, who might not exist anymore when the signal gets there, and who cannot practically respond in a way that matters to you. Meanwhile, you could have spent that same energy increasing your internal processing, your simulations, your own subjective richness. So a rational, highly capable species could quite calmly conclude that large-scale external communication is a waste of their time. There is another angle too. The very concept of a signal you are looking for is structured around your own communication styles, discrete messages, patterns in radio or light, information encoded in sequences that tools like yours can parse. An alien mind might not slice the world into sender and receiver at all. It could treat the universe as something to be modeled and absorbed, not something to be talked to. Its communication could be purely internal, running models of possible others without ever reaching out, because that is cheaper and safer than actually interacting. So when you go looking for intelligent life, you are really looking for a very specific thing. Talkative, primate-style minds that build telescopes and radios, share some of your curiosity, and choose to express that curiosity using technologies and frequencies similar to yours. You're not looking for intelligence in a general sense. You're looking for a reflection of yourself stretched across light years. The problem is, the universe doesn't owe you that reflection. It can produce minds that are sensory aliens, conceptual aliens, and value aliens in ways that break your assumptions. They might not care about the stars, might not care about colonizing space, might not care about being noticed, and might not have any reason to leave obvious fingerprints in the data you know how to collect. From that angle, your whole question, why can't we find intelligent life, might be misaimed. You have defined intelligent life as beings who behave in certain human-recognizable ways at astronomical scales. If most alien minds do not choose those paths, then you will look out at a galaxy that is actually full of thought and call it empty, because none of that thought aligns with your detection filter. And even if some of those minds do know you exist, and even if they could contact you, there is one more possibility people like to bring up. Maybe they have already decided not to. Maybe the silence is not just an accident of physics and probability, but a policy, a choice, or a fear. That's where ideas like the zoo and the dark forest pictures come in. Stories where advanced civilizations either watch you quietly or hide from you completely. People hate randomness, so when they stare at a silent sky, they reach for stories that turn it into a plan. And two of the biggest ones are the zoo idea and the dark forest idea. The zoo hypothesis says this: advanced civilizations already know you're here, and they decided not to talk to you. They watch from a distance, maybe with hidden probes or remote observation systems, but they avoid direct contact on purpose. The motives vary depending on who tells the story. Some versions say they're being ethical, letting you develop without interference, like a wildlife reserve where you don't disturb the animals. Others say they're running experiments, seeing what happens if they leave you alone. Some add rules, a kind of prime directive where contact is only allowed after you cross some threshold, like interstellar travel or a certain level of social stability. On the surface, this neatly explains the silence. You don't see big beacons, you don't see megastructures, you don't get clear signals because those are all turned off around you. You're inside a controlled bubble. The problem is that, as an explanation, it can absorb anything. If they never contact you, the story says that's because they're following the non-interference rule. If one weird event looks like contact, the story says that was a rare test or a mistake or a special case. If you find nothing at all, the story says they're extremely careful. There's no result that clearly tells you the zoo idea is wrong. The dark forest hypothesis takes the opposite emotional tone, but it plays the same logical game. In this picture, the universe is dangerous. Every civilization knows that revealing its location to unknown others could be suicidal. You don't know who is out there, what they want, or how they behave, so the safest strategy is to hide. You keep radio emissions low, you avoid building obvious megastructures, you mask your waste heat if you can. And if you detect another civilization that is loud and careless, you treat it as a potential threat and consider destroying it before it destroys you. In that kind of galaxy, everyone is armed and paranoid. Silence is not a mystery, it's policy. You are the weird one, a young civilization that has just started shouting into the dark without understanding what else might be listening. From this perspective, your early radio broadcasts are like firing a flare in a hostile jungle. The prediction is not that the universe is empty, but that it's full of nervous, quiet, heavily defended societies trying very hard not to be noticed. Now look at both ideas from a scientific angle. Their practical consequence is the same. You can't actually test them in a clean way. Both predict exactly what you currently see. No clear, unambiguous signals. If your radio surveys and telescope searches find nothing obvious, the zoo hypothesis says, of course, they're deliberately staying hidden and watching you. The dark forest hypothesis says, of course, they're deliberately staying hidden to survive, and they've decided not to talk. If at some point you do pick up something that looks like a real signal or see something that looks like obvious engineering, both hypotheses still twist to accommodate it. The zoo story says this is the moment they finally chose to reveal themselves, or this is one group breaking the rules. The dark forest story says this is an outlier, a civilization that's either reckless, desperate, or extremely confident. There is no observation that conclusively kills either model. That makes them poor as scientific explanations because good scientific ideas should rule out some possible observations and risk being wrong. But that same flexibility makes them powerful narratives. They give you a way to emotionally organize the silence. The zoo story lets you feel watched, maybe protected, maybe judged. The dark forest story lets you feel threatened and special at the same time, the loud, naive newcomer in a quiet, dangerous galaxy. Both stories give the silence purpose. They replace random, cold probability with intention, with hidden rules and strategies. From the standpoint of your actual situation, though, all three possibilities, zoo, dark forest, or indifferent universe, put you in the same place. Whether advanced civilizations are carefully observing you, carefully avoiding you, or simply not there in your region and time slice, you still don't have a clear, testable path to finding anyone. You can send messages, you can listen, you can search for weird infrared signatures and strange radio spikes, but you can't force an answer out of the sky. That means the silence you see right now might not be a puzzle with a clever solution waiting at the end. It might be a boundary condition of your existence, a built-in limit of what a young, local, fragile civilization can learn about the rest of the galaxy with the tools and timescales it has. You want the universe to be a conversation. Physics and statistics may have set it up as something closer to a monologue, and that leads to the most unsettling possibility of all. After counting all the filters, all the hazards, all the time mismatches, and all the ways minds can hide or fail, you have to consider that you might not be missing anybody at all. Maybe you are early. Maybe you are one of the only ones. Maybe the main reason you don't hear other voices is because there just aren't many, yet or ever. Here's the possibility most people really don't want to hear. The universe might simply not be ready for other civilizations yet, and you might be one of the first or one of the only ones. Start with how habitability changes over cosmic time. The first generations of stars were almost pure hydrogen and helium. Heavy elements like carbon, oxygen, silicon, and iron are made inside stars and spread out when those stars explode or shed their outer layers. That process takes billions of years. Early galaxies had low metallicity, which means fewer of the elements you need for rocky planets, complex chemistry, and eventually biology and technology. As stars live and die, they enrich their surroundings. New stars forming later get more metal-rich clouds, which build more solid planets, more diverse chemistry, and more chances for life. So your era sits in the middle of that buildup, not at the end. Many models suggest that the peak of cosmic habitability, the time when most long-lived, metal-rich, stable systems exist, may actually be billions of years in the future. Red dwarf stars, which are small, fuel-efficient, and metal-rich, can burn for trillions of years. That means the main wave of Earth-like planets, with stable surface conditions and long time windows for life to evolve, might still be coming. If that is true, then you are early. You are looking for neighbors in a universe that has only just started producing good real estate at scale. Now fold in simple statistics. The Milky Way has hundreds of billions of planets. Even if the full chain from planet to technological civilization is incredibly unlikely, say 1 in a billion or worse, that still gives you a small but non-zero number of successes. In a big enough sample, extremely low probability events happen sometimes. Earth might not be typical at all. It might be one of the rare cases where all the filters lined up just right earlier than average. Being that outlier means that when you look around now, you don't see peers, not because they will never exist, but because most of them have not had time to form yet. This is where the idea of a great filter comes in, a step in the chain from simple matter to spacefaring civilizations that is so hard that almost nothing gets past it. You can put that filter in different places. If the really hard step is abiogenesis, the origin of life from non-living chemistry, then almost no planets ever get microbes. If the hard step is something like the jump to complex eukaryotic cells, or to multicellular organisms, or to technological culture, then almost no biospheres cross that threshold. In all those cases, the great filter is behind you. You are on the far side of a huge bottleneck. If that's true, your situation is unique and unsettling at the same time. On one hand, it means you are incredibly lucky. Out of all the worlds that formed, almost none made it this far. You are one of the few that did. On the other hand, it means the galaxy is mostly quiet not because civilizations die, but because they never appear. You might be one of the only technological species your galaxy will ever see for billions of years. There's no crowd to join, no busy interstellar network to tap into, because almost nobody else got through the hard step. The alternative is worse in a different way. The great filter might not be behind you, it might be ahead. That would mean getting to your current level, global industry, nuclear weapons, synthetic biology, AI research, planet-scale environmental impact, is not the hard part. The hard part is surviving it for a very long time, without wrecking your biosphere, collapsing your civilization, or locking yourself into a permanent low-tech state. In that scenario, the reason you do not see many advanced neighbors is that almost every civilization reaches something like your current stage and then fails. Maybe they trigger runaway climate change they cannot fix in time. Maybe they fight large-scale wars with weapons that permanently degrade their environment. Maybe they build powerful AI or other systems they don't fully control. Maybe they just gradually overuse their resources, hollow out their capacity to sustain high-tech infrastructure, and slide back down. However it happens, their visible phase stays short. They never get to become million-year, stable, outward-facing civilizations. They flicker on, they build some technology, and then they go dark. From your point of view, both placements of the Great Filter answer the silence, but they send very different messages. If the big difficulty is behind you, then the night sky is mostly empty because almost no one else made it this far. You are rare, maybe extremely rare. If the big difficulty is ahead, then the night sky is mostly empty because almost everyone like you eventually fails, and you are standing close to the dangerous edge right now. Pull everything together. The galaxy is vast, with stars separated by tens of trillions of kilometers, tens of trillions of miles. The habitable zone around each star is a narrow range. Planetary systems are chaotic, with migration, bombardment, and long-term instability. Atmospheres are fragile. Life may be common, but the path from microbe to mind is slow and uncertain. Your detection tools are built for planets, not people, and your search covers a tiny slice of frequencies, sky, and time. The speed of light locks in long delays and extreme energy costs. Cosmic hazards can reset biospheres. Civilizations can be short-lived, quiet, or inward-facing. Alien minds may not care about being noticed. And on top of all of that, the big statistical filters may mean that very few civilizations ever exist at the same time, in the same region, with the same kind of detectable technology. So when you ask, why can't we find intelligent life out there, the honest answer might not be, we just haven't looked hard enough yet. The honest answer might be, for a species like yours, with tools like yours, at this early point in cosmic history, in this particular corner of the galaxy, finding anyone else is effectively impossible. Not just difficult, not just unlikely, but blocked by the combined weight of physics, probability, and timing. You are here, which means the universe allowed at least one technological civilization. It does not follow that it will hand you a second one to talk to. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. If you enjoyed the video, consider subscribing to the channel and like the video.